So thank you very much for joining this P4 on data plane programming both. This is a meeting that was organized thanks to Ivana team, who is the work package leader of our network technology evolution package, and Mauro Campanella, sorry for that, and Frederick Flores from Renater. It's a part, in fact, of TNC21. It's a side meeting of TNC21. So we will have a first sessions where we will, in fact, look at different use cases. We will see first a rare from Frederick. And after that, we will see also an implementation of GÉANT P4 Lab, thanks to Jordi Ortiz from University of Murcia. Cristina Clipel-Dominici and Rafael Guillaumarais, sorry for the pronunciations, will present us a very interesting data plane implementation that is called Polka. And after that, Mauro Campanella will talk about INT and the benefit of it. We will have also a presentation from Yatis Kumar from ISNET. And after that, we will see an implementation that is in production. It is a packet broker from Alexander Gal. Sorry, I write Alex, sorry for this. After that, we will have a coffee break, and Mauro will chair the second session, in which we will see two position paper and two short presentation, one from Marinos Dimolianis from the University of Athens, and another one from Arve Newman from Caltech. After that, we will have a discussion mainly focusing on how we could, we have now, I would say, a very nice result. Some different implementations that is are in production or very close to production, how we can speed up the uptake of this technology. What would be the best strategy? What would be the best use cases? How we can build expertise, share best practices, and possibly identify the gaps that we can solve. And with this, of course, just your feedback is very important in the both, of course. So do not hesitate to use the chat if you have some questions for the speakers. Keep in mind that there will be an open discussion during the session too, and we will take in consideration your feedback, because it will help us to lead our next work. So with this, I will leave the floor and ask Frederick to present to us router for academia and education, on research and education, the RARE project. Frederick, the floor is yours.
Thank you, Xavier. So let me share my screen. So you should see the screen. That's great.
Yes.
Okay, thank you. Thank you for being here. I will present with Jordi Ortiz some elements related to RAR, which stands for Router for Academia, Research and Education. So one thing that is quite important. Sorry, first I have some. The first thing I would like to remind is why we are all doing this in the RAR project, because this is something quite heavy and very disruptive. But why we are doing this, and I would like to hammer the problems, some problems we currently have or had, and some observation that you will see that the subsequent presentation will cover some of these points. So first of all, we see more recently the rise of and the need of network-aware application. And usually we use the hop-by-hop paradigm to transfer one packet from a place A to B, but now it is more crucial to be aware to switch traffic flow application based on application behavior. And this is a clear need that we see more and more, especially in the R&E, where, for example, we have some initiatives trying to identify flows within myriads of flows and try to establish a different processing based on this type. The second thing I would like to remind is that the current procurement lifecycle workload that is related to network management acquisition. I'm not sure if it is the case for you, but in Renata, for example, if it is a 5-year experience, and that is a huge hurdle for us. What does it mean? It means that you spend 1 year trying to study following the technology. You meet the vendor and etc. And then the second thing is to prepare effectively the procurement, which lasts 1 year for us. The second, after that, you have the answer. You need to select one winner, and then you deploy the network, and you start implementing everything in your network. So it's another 1 year, and then you are free 1 year to try to improve the system, and then you are good to go again in this cycle. So the net result is when you have a huge team that is and that you are organized for that, this is great. But if you are a very small team that's most of the time can do a lot of things in parallel, different things, you cannot afford this type of stuff. So this is actually our case. One problem is related to vendor lock-in. I recall a story where someone from our community based his DDoS mitigation system on a specific hardware. And once everything was settled, the umbrella system was working great and so on. The vendor just told him that the next year the hardware would be end of life, end of solution, and there was no way for them to have it maintained afterwards. So the net result is that they were locked in this situation, and they had to find a way to still provide this DDoS mitigation system, but with another solution in a hurry, of course. The fourth point is the ability to implement other features. Sometimes you need some specific feature that will solve your solution, that will solve the situation you are currently facing. And the problem is that in this situation, no one will implement this because no one needs this, but except but you. And this is something that is funny. For example, I will just give you an example. If you have a DLNA equipment in your premises or at home, DLNA Alliance assume that everything is in a flat VLAN. So basically, if you have a VLAN, if your home or institution has several VLAN, the DLNA equipment cannot discuss all together. Into the RA-free router project, using the DPDK flavor, we have a UPnP client server discussion. So what does it mean? It means that with this solution, DLNA equipment can broadcast their probes, which is detected by the DLNA server, and then relay this to the other DLNA client on other VLANs. So this solves the solution, but you will find this nowhere except in free router. And the last point is a bit more societal, has a societal aspect. The idea would be to reduce the digital device. The price tag of this solution is obviously, you will see it is obviously less and require less budget compared to the traditional vendor solution. And the idea would be still to provide an affordable network solution, but still without any functionality trade-off. So what is RA actually? RA is proposing to create a unified and open source routing platform powered by multiple data plane that fits our any use case. The thing that was not the case, before is that now everything, all the control plane, the data plane, and the interface between the two is programmable. But more importantly, now you are able to create applications that manipulate packets at 12.8 terabits per second, which was not possible 3 years ago. So the idea here is that in order to engage the discussion, the idea is that we have acquired a tremendous amount of knowledge that we are able to share with you. And the idea and the method we adopted is make easy parallel development, and we can even, with the same total framework, create different appliances. And Alexander Gall create a packet broker that is actually, if you look at the structure of the code, it's actually 95% of the same software used, except the packet broker. So this is the idea. One basic idea, for example, we can reuse this box and have a mitigation box that is able to mitigate 1.6 terabits per second in and out. And if for any reason one person in the audience has a very AI powered solution able to recognize which flow is malicious or not, just tag it, fill it into this box, and you have a very serious DDoS mitigation system. Thank you.
Thank you, Frederick. Thank you for being also very synthetic. Is there any questions for Frederick? Because we have a couple of minutes. In the meantime, so we will reshuffle a little bit the agenda because Yatish is not available. Unfortunately, he has a small trouble. So I propose that this presentation will be the next one. No question for Frederick? Okay. So Frederick, can you free the screen on anywhere? If you have any question, we can have it during the second session. Yatish, would you like to share your screen, please?
Yes, thank you very much. Sorry, I'm now struggling with screen sharing, but I will start.
No problem.
Share screen. Oh, I see. Okay. There we go.
We cannot see it for now.
Yeah, I think I'll just speak without slides because I only have one slide.
I can share it for you if you want.
Yeah, it's the presentation I sent you last time.
Yeah, perfect.
Yeah, okay.
I hope it is the appropriate file.
Okay. The second one that I sent, yes.
It's GÉANT DP both?
Yes.
Okay, perfect. Okay. Is it good?
Yes, this is good. Really my sort of news to the group is that we've been working on using FPGAs in order to bring basically P4 programming into production at ESNet. And so in the last several months, we actually have this system now working live. So it's at a reasonably high quality in terms of implementation. And in the process, we've basically confirmed that all of the pieces that are needed in order to make this work on a Xilinx FPGA using the Xilinx P4 compiler are actually functional and in place. So there's a lot of software that was done and it all works. And so given that that's the situation, I think it's quite reasonable to say that if people wanted to go down this path of using FPGAs in order to build data plane programs, and they wanted to emulate our system, we can certainly provide a lot of guidance as to how to get there very quickly. and confirm that you can get all this stuff from Xilinx and get it running. One of the big advantages of doing this stuff in FPGAs is that unlike, say, the Barefoot platform, the FPGA is stateful. And so we can add extra functionality into the FPGA that might not be normally available in a P4 system. And a lot of it has to do with keeping track of state, identifying flows, and then tracking flows, counting statistics on flows, and things like that. Those things, I think from previous workshops we've seen are possible, but difficult using the register mechanism in standard P4 switches. But on FPGAs, no problem at all. And so if you could go to the next slide, what I'm suggesting is, next slide. Slide 2.
I am on the slide 2.
Okay, just a bit of lag here. I think it's a long distance to Canada.
Okay.
I think what's possible now is to start thinking about control planes that can be connected to this P4 data plane. So I would estimate that within a month or so, somebody could get the data plane running with a little bit of help and an FPGA card. But the outstanding work now is to build a better control plane in order to connect to the P4 system. In the Xilinx world, there is no P4 runtime. There's sort of a low-level access to the tables, which allows you to directly program your own P4 tables. But obviously, as we know, we need controllers that go on top of that match up with whatever function you're trying to do. So at ESNet, we've implemented the telemetry function, but there are other easy things that can be done, like DDoS mitigation at 100 gigabits and so on. All of that is possible, and it's something that we could help people by talking to them and get them started and so on. One of the really interesting capabilities of these FPGAs is that they have high bandwidth memory. So they have 4 gigabytes of very fast memory that's on chip. And so they're able to implement very large hash tables that are very fast. And so, for example, we did a quick experiment where we could put in IPv6 ACLs, and we could put 60 million of those ACLs into the device. And so for things like security applications and enforcement, the capacity of that ACL machine is pretty incredible. And so that's all I have to say for today. I think certainly if anyone wants to pursue this line of thought, feel free to reach out to me, and I'd be happy to answer any questions right now if people have any.
Thank you, Yatish, for this presentation. Is there any question for Yatish? I have maybe a question. Is you mentioned that you envisage that DDoS detection and mitigation could be possible to be implemented on FPGA card. One of our team has encountered discovered some limitation on the Tofino chipset due to the fact that there is not a lot of memories that is necessary to implement the DDoS counter DDoS algorithm.
Yes, I understand that very well. And so in addition to DDoS, at LBNL, the lab, they use Bro in order to provide blocks against specific attacks. And their current count is about 10 million blocks are installed at any given time. And so to put 10 million ACLs into any routing scale device is very difficult. And they actually ended up buying Corsa switches, which I built in my previous life just for that reason, because we could do that in those switches. But now with these FPGAs, you can get a much less expensive device, and actually with higher capacity than even the Corsa switches used to have. So I think that's definitely one of the corner cases where FPGAs can do something that's almost impossible, either using a standard router or white box for sure.
Okay, thank
Yeah, the P4 program for that is actually trivial. It's a single table P4 program that says, match on a TCAM 5 tuple, and if you get a hit, drop. And so it's a very simple program to write. And given that we have all this infrastructure working, it wouldn't take more than a few days to actually get something like that up and running.
Okay, thank you very much. Any other question?
So Yatish, the server you are using are powered by PCIe Gen 3 or PCIe Gen 4?
It's dual mode. So it's Gen 4 by 8 or Gen 3 by 16. So the bandwidth is always 100 gigabits. But it has 200 gigabits on the QSFP side. And so sometimes we use it in wire mode where the packets come from the left and then they come back out. And we can do 100 gig wire for mitigation, for example, without sending anything into the PCIe. The PCIe is just there for control. And then there are other applications where we send the packets all the way through the PCIe. It looks like a standard Mellanox NIC at that point. And actually, one of the big achievements in the last month is that we have DPDK running against this now. So what you can do is you can put this NIC card in, you say replace your Mellanox card with this card, treat it like a 100 gig NIC, and access it using DPDK. But on the NIC card, of course, you can do all your P4 programming. So you can first hit your packets with your P4 program. You can, statefully do things with the packet if you like, and then send the result up to DPDK just as you would on a normal application.
Excellent. That's great achievement. I would be curious to have some feedback or documentation on it. Just to let you know that we have discussed with Intel, of course, and the future, of course, now is Tofino 1, 2, and 3, but we will see soon new targets with Tofino ASIC coupled with FPGAs, Intel FPGAs that would be specialized in doing more specialized things like encryption or for if you need, for example, MACsec encryption and put it in a wire, and also the work you are doing now with Xilinx, and that's quite interesting because I think that best of both worlds can be used as a Lego brick and provide very serious application, even if they are developed in parallel independently.
Yes, I agree. I think because of the way the market is, we've arrived at a place where you need both. You need the FPGA for stateful processing, which Intel has recognized as well. And so I know that there is like a 1U form factor switch probably coming that'll give you embedded FPGAs. And then there is this form factor, which is NIC card based, which allows you to do slightly different things. So yes, definitely. I think both companies have now got good solutions coming for data plane programming that way.
Out of curiosity, did you have a chance to get access to NVIDIA GPU or other Mellanox type switches powered by Spectrum B2 or V3 ASIC?
Oh no, we don't have the resources to chase that type of stuff down. It takes a lot of time and effort. So we picked our platform, and we've been sort of sticking with trying to make what we chose work. So I don't have direct experience with that. I think one of the things that Mellanox does is confuse us a lot, often by talking about the blue field. The ARM processors on that card can only do control plane offload, or very limited, say 1 gigabit of data plane offload. If you want to do 100 gigabit programmable data planes, then the FPGAs are the only solution I know of, other than, of course, the Tofino. And so to me, we don't have applications that are related to control plane offload. It's always full speed, 150 million packets per second, 100 gigabit data plane stuff. And there, I think this is the only choice.
Thank you very much for this presentation, Yatish. Very interesting.
Yes,
Mauro has a question.
Yeah, just two comments. One is that about DDoS and security. I think that the breadth of security threats that they are facing mostly requires a careful choose of the algorithms and what you want to do to fight in the right way the DDoSes. This is our experience. Simple DDoSes, extremely distributed, high throughput attack that's threshold based, and that is perfectly the FPGAs and everything are perfect at that. But if you want to get out more information how who is attacking, or you have a different type of attack, which is a distributed attack, then the amount of memory used in the data plane to actually memorize and combat the attack has a profound difference. So the second comment is that in my experience in what we are doing, the raw silicon is clearly very, very important for what we do. But the other point that we have probably chances to work together is the algorithms that we want to implement on that silicon, because that made the difference.
I agree a lot. I think this is the fact that we can, put 60 million blocks it's just the simple tool. What blocks do you want to put in is the complicated question. And at least from my previous life, it wasn't 100 gigabit attacks that were happening. There were still 1 gigabit attacks to take down a high school, for example, or there were application-specific attacks to take out a mail server. And so it's not really high volume as much as being able to follow the source addresses of whoever is trying to attack you. And so good strategies for following those relatively slow attacks with large memories, I totally agree. And I think this is just a tool to enable the research on the control plane for that. Yes, I agree.
Thanks, Yetish. Yeah, that's I added a word in my presentation, which is knowledge. I think we have to still develop some type of correct knowledge to use these very powerful engines. Thanks.
Yes, for sure. Yeah.
Thank you very much once again, Yetish. Thank you for the question. We will come back to our agenda. Jordis, if you can share your screen, please. Jordis is from professor from University of Murcia, and he's working for RARE, and he will present us GÉANT P4 Lab.
I hope you can see now the presentation full screen.
Yes.
Okay. Yes. So thank you for the introduction. I'm going to present the GÉANT P4 Lab with Frederick, of course. Basically, what is the motivation to have this kind of lab, right? So Frederick was already introducing the work we are doing in RARE, which is to offer a data plane at a really high line rate, right? So that with the simulators and in this case, looking at P4 with BMB2, you are just limited to what your CPU can do, right? So there was a need for this hardware in order to test that what we were doing could be really achieved at a really high speed. So with that in mind, we set up a lab so that we could test all the algorithms and all the protocols that we were implementing. And then we came to the conclusion, so why not share it, right? So that now that we have this deployment and that is available to us, but we are, of course, sometime we are developing and we cannot use it at that moment. So why don't share it, right? So basically, there is a deployment which is through Europe. We have 4 boxes in Amsterdam, Poznan, Frankfurt, and Budapest, and those are the connections between them that are provided by GÉANT. And with this core 4 boxes, we have other connections to people which are working with us. So we have boxes in University of Murcia, we have boxes in Renata. I mean, they are owned by them, but they are connected to the lab, so they can do experimentation directly with these boxes. So you can do your own P4 program, put it on the boxes on Europe, and make your packets go through them and see what is the delay and how they are working, and if they are working at line rate, and if there is any problem with them, and if they are performing as you are expecting, right? So And this is basically, as I was saying, the deployment we have. And then for that, we have, we of course wanted to offer the people that was willing to work with us with a good experience in terms of when can I use it, how can I use it, how can I access it, is it available now or not, when it will be available. So basically, we have developed within the project this network management based on NMAS. So we have Bastion server, which gives access to the users to the boxes themselves. So basically, you are able to schedule or to book the availability of the devices themselves, and then automatically you will have access to those boxes. So for that, we have a booking mechanism in which, as I was saying, you just say which of the boxes you want to use. You say what is your time schedule, and that will automatically provide with the keys, with SSH keys to the Bastion servers to which you will connect, and then you will have access to those boxes. On those boxes, you will be able to build your own P4 program, put it into shape, so have your own control plane, and have the traffic going through it. We have a couple of GTS nodes you can use in order to inject traffic inside the lab. And of course, you can always use one of the other boxes from our partners if you arrange that with them, or you connect directly to the P4 Lab with a VLAN, so that you can just put your traffic inside of it, right, and get it back, or have a couple of connections. So basically, as I was saying, you will have this kind of reservation mechanism. You will know when you will have it available and during how much time you will have it available. And just having a VPN connection, you will be able to manage those boxes by yourself. You can do with the boxes whatever you are planning to do with them. So it's not limited to any kind of program. So you can, of course, do any kind of experimentation. So we are inviting you to join the lab, either because you want to start your experimentation on P4 on real hardware before getting some for yourself. So you are, of course, more than welcome to start building your own P4 programs on it, or just the ones that are already available as examples. Or you can, of course, test RARE. We invite you to test what we are already doing. So we will put for an image of RARE for you already on the P4 Lab, and you will be able to check the capabilities of RARE on P4 hardware. Of course, you can experiment with people around the world. As you have seen in previous slide, we have connections with Starlight. We have connections with UFES. You will have some presentation afterwards about it. So we have connections with a lot of people with which you can do some work. Or, as I was saying, you can connect yourself and be part of the laboratory. That doesn't mean that you lose the capability to do whatever you want with your box. But in some circumstances, of course, it's really interesting to have direct connection to this kind of lab, so that you can extend your capabilities at your premises with the ones from the GÉANT P4 Lab. Finally, I want to invite you to join our demo. It will be held on the 24th of June within TNC at 20 to 12. So, and there we will show how this reservation mechanism works, how you connect to the boxes, and also we will showcase a bit RARE and how we managed to do some 1 terabit, 1 petabyte in 2.5 hours transmission with it. That's it.
Thank you, Jordi. And good luck for your demonstration on the 24th.
Thank you.
Any question for Jordi? No? Okay, so yes, you will see that that RARE is able to take benefit of all the forwarding capacity of the Tofino. That's very very instructive. If there is no question, we can go to the next talk, Christina. Before you share your screen, I will just share my screen just to introduce your talk. And the talk says that your work on Polka has been awarded by the Google Research Scholar Program,
Yes.
of course, in the networking categories. So congratulations, and I leave the screen, and please, can you give us an insight of this Polka algorithm? Thank you.
Thank you. I will present today our proposal that's called Polka. That's the acronym for Polynomial Key-Based Architecture. It's a source routing proposal. The original proposal is a work from Federal Institute of Espírito Santo and Federal University of Espírito Santo in Brazil. And we are collaborating with the RARE project. So there are other people involved now, Frederick from Renate, Jod from University of Mercia, Trinity College Dublin, Elwin from HitNet. So I'm going to talk about this experience. So the motivation of our work, this whole context of SDN and programmable network device, which enable a group to prototype and deploy a completely novel and innovative protocol. And in our case, we are tackling the challenge of how we can select paths and load balance between them to adapt to variable workloads. So the common solution for this problem, normally you encode these paths in core nodes as forwarding table entries, and then an edge will select among these table entries that are already there available in the core nodes. This traditional approach has some problems because you have a large number of states. This can cause a management burden. The switch tables have restricted capacity. So normally the traffic engineering cannot exploit all the available paths from the topology. And also there is high latency for path setup, as you need to some convergence time to reconfigure the paths. So a solution as an alternative to solve this problem is source routing. In source routing, a source specifies the paths, the nodes in the path, and put a route label in the packet header. The traditional way to do this is to encode a list. So you have a list of output ports. Then each node will perform a pop on this list and take the port of itself. The problems we can see with this approach is that you need a rewrite operation, and it's also very difficult using a list of output ports to enable complex applications. So if you want to do applications with multiple paths, or if you want to do fast failure reaction, the encoding in a list is not very adaptable to complex use cases. So our problem that we want to tackle with our research is that, is it possible to define a fully stateless source routing approach? And by that, we mean we don't want to do packet rewrites, and we do not want to use tables. And we also want to offer support for complex networking use cases. So with that in mind, we proposed, the original proposal was proposed in NetSoft last year, the original paper. The main idea behind our proposal is that instead of using a list for source routing, we use a arithmetic operation to do the forwarding. And this operation is based on the Chinese remainder theorem and residual number system. At that time, we didn't have access to real hardware, programmable hardware. So our proposal was based on an emulated proof of concept. We use BMV2. We also explored some metronome SmartNICs, but they didn't have the capacity, the functionalities we need. So it was the original proposal, and to really prove it on real-world environment, we need the hardware. Programmable hardware with the specific capacities. So we had this opportunity to talk with the group from RARE, and we started to collaborate, not only to have access to the testbed, but also to discuss the research problem. And it was very, very nice experience. And we could, with this experience, we publicated a paper that will be presented in ONDM this year. The paper is called Deploying Polka Source Routing P4 Switches, where we describe the experience of deploying our idea and porting the original solution to GÉANT P4 Lab with the use of the Tofino switches. So in this paper, we describe how we could perform the modifications we had to do, and the experiments and the evaluation of this real-world deployment. So Polka architecture involves a service layer and a control and orchestration layer, and the physical infrastructure layer where we have the P4-based data plane, composed by edge and core switches. And in this prototype, in the phase we are now, we are more focused on the data plane, but we are expanding also the control plane functionalities. So the main idea with our proposal is that we can discover the output port and execute the forwarding in the core switches using a simple remainder of division operation that's called a modulo or mod operation. So the port ID is given by the remainder of division of a root label divided by an identifier that we call node ID. That's the identifier of the node. So each node can discover the output port by dividing the root ID in the packed header by its own node ID. The challenge we faced here is that the P4 language does not natively support the mod operation, but we could solve that problem by reusing the CRC hardware. So, and the Tofino native architecture, the TNA, it supports you to configure the CRC polynomials. So we could execute this remainder of division operation by reusing the CSC, and we could, with this idea, deploy our proposal in Tofino hardware. So I will explain in the next slides a concrete example, so it's easier to understand how our proposal works. So in a network configuration phase, a centralized controller will assign some identifiers to the nodes. So each node will receive a polynomial, and the port labels will also be represented as polynomials. And after this network configuration phase, when the flows start to arrive, the controller will choose the paths for each one of the flows. So a path here is represented by a set of switches and a set of output ports. So in our example, in red, we have the identifiers of the nodes, and in blue, we have the identifiers of the output ports that the controller has chosen for this specific path. With this path, the controller can calculate using the Chinese remainder theorem. The controller calculates the root ID, and with this root ID, it can install the flows at the edges. In this example, using the Chinese remainder theorem, the root ID calculated was this one here in yellow. So the controller will install will install the flow entries here. The edges will be responsible to add this root ID to the packet header. So in each of the nodes throughout the path, the nodes will execute a very simple operation. That's the mod operation. So the mod operation of the root ID by the node ID will give the remainder, that's the output port. So the root ID 10000 divided by the node ID of the first node, that's 11, gives remainder 1, so the output port is 1. So all the nodes in the path will perform this operation, this mod operation, to discover the output port. It's important to note that there is no packet rewrite. The root ID is the same for the whole path. We don't use tables. And performing this mod operation, each node will discover the output port. And finally, when it reaches the edge will remove the root ID, and the packet will be delivered to the application in a transparent manner. So the application will not have knowledge about the Polka routing that is happening in the core. So we had this original proposal. The original proposal was implemented in BMV2 in an emulated environment. With this collaboration with the RAP project, we were able to port our code to TNA, to Tofino, and we built a prototype using the GÉANT P4 Lab. Here we have a picture of our prototype. So we used the 4 nodes that are geographically distributed in Amsterdam, Frankfurt, Poznan, and Budapest. We assigned the node IDs for each one of these switches, and also the port IDs that are connected in this topology. So for this topology, we have a shortest path and a longest path in blue and red.
Christina, you have 2 minutes.
Yes.
Thanks.
Yes. So we had some preliminary results for throughput and forwarding latency. So it was very nice that it was the first time that we could really evaluate the performance of our proposal, and we could see that our performance matches the performance of traditional table-based and list-based approaches. We also are performing some path reconfiguration experiments, so we can prove that when here in this example, we can migrate from the shortest to the longest path with minimal interruption, because for source routing, you only have to change the root ID that the edge is adding in the packet here in H1, for example. And if you put another root ID in the packet, you already migrate to the other path without having to do any configuration in the nodes in the middle. So future works. We are now, this was the prototype that we did in isolated manner. And now we are also working with Frederick, Jord, and the group of RARE to integrate our code into the RARE repository, so other experiments would be able to use Polka if they want, because the code will be already available there and integrated with their code. We are extending our control plane functionalities and preparing some deployment guidelines for production use cases. We are also exploring some very interesting properties of Polka and these RNS system for security, multipath routing. For example, with this representation, if we just change the meaning of the output port with polynomial to represent not the port labels, but the port states, so the transmitting states of each port. So if it's 0, it's not transmitting, 1, it's transmitting. We can use this almost the same approach for multipath and not only for single paths, unicast. And we are also exploring some interesting ideas. The polynomial representation can use polynomials of higher orders, not only binary polynomials, to explore multi-layer networks. We can use multiple keys for protection paths, QoS. We have already applied this for service function chaining. We can use hybrid operation with table-based approaches to safety CAM, and explore more this very important property of agile path reconfiguration in the edges to provide more agile path reconfiguration for dynamic workloads. So sorry if my presentation was a bit long, but this is the idea of our proposal, and also the description of this very nice experience of deploying these in collaboration with RARE.
Thank you, Christina, for this very interesting presentation. That demonstrating the fact that we can program is, I would say, a driver for new ideas and a driver for innovation. One question, maybe just one question, is someone? We are very late. But...
I have a question.
Yes, please.
Did I understand well? I mean, this is extremely interesting, both from the point of view of performance, but also related to what I will talk about. If I understood well, the state variables can be anything. In other words, if I have a complex problem, like a science program with many flows, many classes of flows, different priorities, different constraints in terms of geography, how things should flow or not flow for organizational reasons, is it right that all of these, I can use any state variables I want, you know, in order to handle the multiple paths and decisions among them? Is that correct?
Yeah. Yes. Because once you put this in, the main difference is that you don't need the states in the core network. So if you put the states at the edge, you can use that state inside the network to do what's important in your application. So we can do this for representing the root itself or other information. For example, we have already explored to use, in the same way we calculate the root ID, we could have a traffic class and put this information here at the packet header. So the edge would include this information, and then the core would calculate the information, not having to maintain a state inside the core node itself.
So my last short question, I mean, and I think I know the answer. So sometimes, especially in these complicated network situations, you want to have an in-network cache. But that would just sort of be like something like an edge, but in the middle of the network. I mean, this could also be accommodated, could it not? Yes.
We could have it. We could have special nodes in the core that are capable of adding new information or modifying the information that's already included in the packet.
That's great.
Yeah.
Thank you.
Can I ask one related question, please?
Oh, yes. At the very last.
Well, I mean, it has to do with how do you implement traffic engineering kind of considerations like quality of service and so forth in your approach. I mean, it appears to me that it's done quite automatically, with all that type of route identification and so forth. And my question has to do with whether you could have in your state approach also some quality of service requirements that could, in a way, emulate something that they do with MPLS and traffic engineering.
Yeah, I don't know if I understood the question, but we have a layer that we call control and orchestration. So the whole intelligence of the topology management, the path computation, and the polynomial generation itself, it's centralized in the controller. And the data plane itself, it's very simple. It just has to perform that simple operations. So the complexity of the traffic engineer would be here and can be viewed as a software-defined application here in the control layer. And we can take benefit of algorithms and proposals that are already used for other works and apply them to our specific data plane.
Okay, thank you. I mean, you understood perfectly the question, and thank you for the answer.
Okay, thank you very much, Christina, once again, and congratulations.
Thank you.
Now we will have the presentation of Mauro Campanella about hint. So Mauro, the floor is yours. Mauro, I don't know if you are speaking because we don't hear you. We see clearly your screen. It's very nice, but cannot hear you. You are muted. I see that you are muted. Perfect.
Can you hear me now?
Yeah, perfect.
Okay, thanks. I will try not to go into any details in in-band telemetry. I just want to tell you why and our experience. Why INT? I think in-band telemetry is one of the technologies that can really bring the data plane programming to an effective monitoring of the network in different ways. Because what you actually do is you manipulate the packets with line rates. And manipulation may imply a lot of things, including adding data, moving data, and so on. If in some way, monitoring of these infrastructures become more and more important because you need to understand more complex infrastructures. Having an agile tool like INT that uses data plane programming to do that may have a benefit on all these technologies. Essentially, so INT is data plane applied to monitoring. It is also useful for another reason, that since it works at line rate, you can really try to understand the behavior of the network at the maximum time granularity in terms of microseconds, nanoseconds. And as I was saying before, we need to understand those networks, especially if we are moving to a terabit range. This is in-band network telemetry in a nutshell, starting from the sending host. The host sends a flow. One of the machine, which can be a line card or a host or a switch, actually manipulates the original packet, adding some information on the packet itself. So it extends a little bit the size of the packet. The packet flows through the network, where another node may add additional information to the same packet, and then flows through the destination. And the sync node actually digests that information, takes out those information from the packet itself and forwards the information for the final destination. The information is collected, stored, and then analyzed. This is what we did on our existing production environment. We acted as end users. We had two sites, one that acted as a source of flow and INT information, and the other just collected the information and digested the information, sent them to the collector, and then very simple setup, but demonstrates that INT is compatible with our own networking, at least from the end user side, if you don't have specialized hardware in the core. The platform used are on the bottom of this picture. Tofino, which is common to Edge Core now, Intel or Arista. Also FPGA, an FPGA based on Chestnut, and the virtual environment, both for BMV2, and now we are finalizing the DPDK version. That's the testbed. The red dots in the European maps are the testbed side, just to let you know that it works. Lesson learned, what we learned from what we did. Essentially, a mixture of platform may be the ideal thing, because you may want to have a simple testing with a low capacity flow, and that can be done even without very expensive hardware. You can have Tofino switches. Each of these platforms has pros and cons. So my idea is that you need to elaborate a little bit on what you are interested in. For example, all these hardware platforms have some limitations on the number of stages per packet. For each packet, if you want to preserve line rate, then there is a limited amount of operation you can do. So if you at the same time want to do routing, switching, and monitoring, then you have to reach a trade-off between the two. It works. And by the way, this is precision of microsecond level of what we got. And it was only 3 megabit per second traffic UDP flow on the network itself, which means that you are really able to go and use a mirror glass to look at what is happening. It's fine in the sense, oh, sorry. It's fine in the sense that the traffic was about 2,000 packets per second in terms of in packets, 3 megabits on the network. The NRN's network, they're very good, no reordering, no losses, production environment. Packet inter-arrival time fluctuates a little bit around the average, which is considered half a millisecond or 550 microseconds, with some jitters. Those jitters are the points in which we need to understand why that happens, and if it is needed, why to improve. No packet losses, so the flow was perfect. Everything was received by the end side, but nonetheless, the traffic, as you can see, is waving in some way. Even to the case that if you increase the mirror glass magnification, then you can see that there are outliers which are very, very delayed. The packets may be flowing normally with a certain amount of inter-packet delay. Then all of a sudden you have a packet which is delayed by more than half a millisecond, and then everything goes back again. Is that back? No, that's function of the, obviously, the application you're interested in. Forward. With the simple setup we had, nonetheless, we can manage flows up to 10 gigabits, even if you want to look at every packet. So we had a very simple setup. You may find, I have a reference slide at the end, so I won't go into the reference, but it's Grafana, InfluxDB, standard tools, Tofino and FPGA, so no exotic things. Nonetheless, the quality of what we can get out of these, not so expensive, I would say inexpensive environment, is at the age of 10 gigabit per second or even 100 gigabit per second with a certain amount of care. If you want to increase the amount of ICT complexities, adding Kafka, for example, or adding more complex load sharing mechanisms from the ICT point of view, then you can really improve and get to 100 gigs. So 100 gigs are in reach, and you can really do things at 100 gig level. Instead of just putting brute force, it is also possible to improve at various levels what you are doing. The exporting can be improved by clever algorithms in deciding what you can export. Same for the collection, in which you can collect multiple packets or information at the same time, so the load of the database is lowered. Preprocessing in data plane to do things and so on. So what I'm saying here is that according to our experience, We are already capable of 10 or even more gigabit per second line rate every packet, but you can even improve that if you look at the algorithmic point of view. You need really to understand what you are interested and what you want to plot and understand. State of what we are doing, we produced a int P4 code on GitLab, is standard one, but is compatible with the main platform. I show it to you, and the DPDK branch will be added soon. Data collection and presentation are the standard ones, InfluxDB and Grafana. Not perfect, but a very good start. The next step is to improve the clock synchronization. The idea is that if you have to look more in details with more time granularity, you want to synchronize better the nodes, because otherwise it's difficult to understand the order of what is happening in our network. And not all the platforms support what I would say a good timestamp tagging in the packet. So a little bit more care about the clock synchronization is needed, at least at the microsecond level. We would like to produce a setup of int, which is on a virtual environment, so that a person can download the images and start using it on a simple tabletop environment and understand the basic functionalities. And the other thing is that I would like, and we would like to do some systematic measurements of the behavior of our network in production using these two. Summary, very short. I think that programming at the silicon level, whether it is an FPGA or a Tofino chip, is not programming as usual. It's a different kind of programming, and that has to be taken into account. It takes some time, even for the programmer, to take into account the peculiarity of these type of programming. However, as it has been demonstrated by the previous presentations, there is a large amount of capabilities in applying this data plane programming, both for testing new ideas and at the same time for understanding better our network. Now P4 is becoming more and more available in various platforms. So what I'm saying is cheaper to start with and to operate. It's a magnifying glass, and this is a function of the type of problem you want to do, but you can really do algorithmics even in the data plane to take decisions in real time. Time synchronization is important. Last but not least, if you really want to exploit the kind of information to understand what you're doing, and you want to do it, I would say, at least at the tens of microseconds level, then be prepared to face a large amount of information, monetary information in this case, that you have to deal in the right way. It's a benefit. Everyone who knows, I think, agrees that having a large amount of information is a benefit to understand better what you need to do and what you need to do at the control plane. Nonetheless, is a different beast in respect of what you're using. And these are the reference table, and I will stop here. So back to you.
Thank you. Thank you, Mauro. Just one question for Mauro. No, if there is no, thank you very much, Mauro. You can, if there is any question or development,
we'll
you can.
Later in the
yeah. We will finish with a development of Alexander Gall that has put in production a packet broker. Alexander is from Switch, yes. The Swiss NREN. Please, Alexander. Thank you.
Yeah, right. So this is an application from the realm of an actual network operator. So this is something that we've been using in production for some time. It's a fairly simple, from a programming standpoint, very simple application of P4, but nevertheless solves a real-world problem in our case. And so I want to start, before I say what exactly it is and what it does, with how I got involved with this and what was the original motivation for me to do this. And our use case is actually a NetFlow export. And back in the old days when routers could basically produce unsampled net flows by themselves, that was not a problem. You just configured it. But these days, when basically all of the routers can only do sampled net flow, it's a problem when you actually are interested in unsampled net flow, which we are. And so we developed the idea that what we can do is, so we only generate net flow from our external connections with neighboring ASs. And so what we do is we use optical taps to get a copy of all of the traffic. And that's where this packet broker comes into play, because it's essentially an aggregation device that aggregates all the packets into a small set of ports that is then connected to another device, which is a regular rack mount server that then actually performs the net flow generation. So that's basically a setup that exists at each of our POPs. So you have the regular router, that's what's called switch border router on the left side. And then you have these passive splitters that couple into all the external links. So for both directions, ingress and egress. And this then goes into this device that I labeled a packet broker, and then that one is connected, in our case, with 200 gig ports to the actual NetFlow exporter. So the main reason for doing this is that the exporter itself, which is just a standard rack mount server, is not suited to have a lot of interfaces. And because we use optical taps, we need 2 ports per monitored external link, one for each direction. And so that is the main purpose of this packet broker to perform this aggregation. But for the purpose of NetFlow, it's important to remember on which original port the packet was received or transmitted on. And so the NetFlow collector can then reconstruct associate the packet with a particular router interface. And so in order to do that, we simply add VLAN tags on ingress. So that is one of the main tasks that the packet broker has to do. The VLAN tag will then be interpreted by the NetFlow exporter to reconstruct that information. So the aggregation, of course, needs to be flow aware. So we have to make sure that all packets that belong to the same flow are mapped to the same physical port. We also have a capability to rewrite source and destination MAC addresses. So that's a thing that is handy when your router has sub interfaces and uses the same MAC address on all sub interfaces of the same physical interface. Then because we use the MAC address to identify BGP peers, in some cases we actually have to rewrite the MAC address to make this unique. So that's a feature that's also there. There's also a feature that lets me filter packets per IP source address. That was added because nowadays there are lots of scanning activity going on, and there can be single hosts that can easily create hundreds of thousands of flows per second just by scanning activity. And so we can filter out these packets and so reduce the size of the flow tables. Now, once I've done this, I realized that actually the box that is located on all our POPs can also potentially do interesting things that has nothing to do with NetFlow generation. So one additional feature that this device now has is what I call a flow mirror. So I can basically specify a rule that matches on some or all of parts of the flow identification, so addresses and ports, and then create a copy of those packets and sends it to an arbitrary port. And so, for example, that can be used to perform TCP dump or packet captures of interesting traffic that crosses our network borders for whatever reason, debugging or monitoring or whatever. The device can also drop certain packets, and if you're interested, what these packets are, you can also, instead of just dropping them on the floor, you can redirect them to a port and look at them and then maybe figure out why they were dropped. So that's the basic functionality that's all implemented by a fairly simple P4 program. And the devices that we are use specifically are the wedge 32-port wedge switches from EdgeCore. They're very handy. They're one rack unit. They have 32 ports. They're cheap. When we bought them, they cost around 6,000 euros per piece. And so that's the only platform that we are currently using. The P4 program source code is available on GitHub. Of course, it's Tofino specific, obviously, because that's the device we're using. And so if you want to build this, you need to have access to the SDE, which unfortunately requires an NDA. But being P4, and it's already a very pretty simple program, so it will be easy to extend that. So whenever you want to use this, not in the context of Network, but maybe have a different use case, it would be pretty easy to adapt it to that. It also has a simple control plane, which is basically a Python script. So the way the Tofino system, P4 and the Tofino system works, so there is basically one daemon running that's doing all the programming of the hardware, and northbound it uses gRPC to talk to the control plane. So my Python script simply takes basically a configuration file and then translates that into calls to this daemon via gRPC that then programs the tables of my P4 program. And to make it useful in practice, also I've implemented a simple SNMP agent, so I'm able to generate regular traffic graphs for all the Tofino ports. There's also a simple command line tool that that you can use even from remote. Actually, that uses TCP to talk to my control plane program. So you can look at configurations or perform certain configuration tasks. So that's basically the software that's there, and all of that is also part of a Git repository that's available. And so the next step was actually, I mean, this is already useful for us internally, and I wrote it myself, so I know how to configure it. But I thought it would be nice to actually create an entire system, an entire appliance that could be used by anyone who has no idea what P4 is, who doesn't even have to be a Linux system administrator, and make it easy for them to use. So I took this one step further, and I created packages, software packages, and I created an installer that uses the regular ONI mechanism that's available with basically all switches that you can buy these days. They come pre-configured with ONI, and so you can install the whole thing in one go. As the package manager, I'm using the Nix package manager. For those of you who know that, is a very powerful package manager that makes it easy to make sure that all the dependencies are always right, and people can reproduce the system very precisely and so forth. And this already all exists and it works, but unfortunately I cannot show it to you, and I cannot give it to you, because right now there are still legal constraints from Intel, because up to this point, so there's still a signature missing before we are able, or we are allowed to distribute the runtime artifacts of everything that comes out of the SDE to third parties, to people who have no license agreement with Intel. That's unfortunate. Should be solved very soon, hopefully. And then at that point, I can actually make all of this additional stuff available. And then that would make it possible for people to pretty easily buy a device and just set it up in one step and then have a usable system, which in fact, that part of the entire development was took me significantly more time than writing this pretty simple P4 program. So this is actually a kind of non-trivial problem to get a system actually to a state where it is distributable and usable by regular people. yeah, that's all I have. Any questions?
Thank you very much, Alex. One question for Alex? Alexander, sorry. So, thank you very much, Alexander, for this packet broker. We are 10 minutes behind schedule, so I propose that we take a break of 5 minutes to take a coffee. And we will restart with Mauro, who will chair the next session. And therefore, we will have a short presentation from University of Athens and from our there also, from Caltech. And after that, we can exchange about how to develop the data plane programming usage. Thank you, and be back at 2025. Yeah. Thank you.
I kindly ask both Marinos and Harvey to keep, if possible, the time so that we have at least a quarter of an hour for discussion. I think it's very important. The BOF's main objective was exactly to discuss how we can work together independently, if you want, on the technical side. We have to have common interest, but how we can best work together to improve the overall results of what we do together, and which are also the challenges and the use cases, that, if you want, the problems we see in front of you, the issues that we want to solve using these technologies. Okay, here's 3:30 mostly. I would kindly ask Marinos to start his 5 minutes presentation.
Hi, hello. I hope that you all see my screen. Yeah, I believe so. So I'm going to start.
We can't hear you.
Yes, we can hear you and we can see you.
Okay, yeah, that's great. So I'll try to keep it in 5 minutes. So
you're muted now. I can see it. No, we still can't hear you.
I'm not speaking now. Can you hear me now?
Yeah, okay, fine, thanks.
Yeah. So today I'm going to talk about this is an outline of our effort regarding DDoS attack classification mitigation using programmable network data planes. So as already mentioned, legacy approaches, or traditional ones, keep maintaining statistics related to source IPs or network flows. They actually store them and analyze them. That may hinder the actual real-time detection. And also the second part is that kind of approaches actually require a lot of number of filtering rules to actually mitigate the ongoing attacks due to the massive number of IP sources. On the other hand, there are some static signatures. These are actually used from intrusion detection or prevention systems, and they match and block specific observed attack patterns. The problem here is that they cannot actually adapt to newly observed attack patterns. To that end, we considered the dynamic signature-based classification and filtering scheme that utilizes high-performance programmable data planes, mainly software data planes, that actually monitor network traffic and perform the actual filtering. And the whole intelligence comes from supervised machine learning algorithms that actually classify the observed signatures into malicious or benign. So in a nutshell, we are using Express Data Path. This is a framework that actually enables a lot of network interface cards to collect and filter network traffic, and also allows the packet field collection ranging from network to application layer. We collect that type of signatures that are observed in a network stream. We classify them using supervised machine learning. Then we try to pinpoint the optimal way that actually can be used to block the attack traffic, actually a concise set of filtering rules or signatures that are going to be deployed into programmable firewalls, also here XTP, that actually filter the network traffic using those salient attack characteristics. we applied as a use case our effort in DNS amplification attacks, in which we actually tried and achieved accurate traffic classification on real network traffic, both benign and malicious, achieving a true positive rate of 99%, a true negative rate of 98%. We identified as a key takeaway that signature-based schemes require less monitoring data than IP-based to filter more attack traffic, as the number of malicious DNS signatures observed in a DDoS attack is much more fewer than malicious IP sources. Finally, offloading the filtering of a DDoS attack in an external middle box utilizing the Express Data Path framework gave us a 5 million packets per second per CPU, both in filtering and monitoring specific packet fields. And also, this is really a nice cloud-native application since it can horizontally and vertically scale. As interesting future directions, we may consider mechanisms for federated environments that actually exchange signatures between them, both malicious or benign. And there are also a lot of nice technologies such as federated learning that enable that to be done in a privacy-preserving fashion without actually revealing sensitive information. There are also nice future direction regarding the collaborative filtering, especially in cases where upstreams could block the DDoS attacks utilizing programmable data planes and also leverage their scalability. And one of a really nice future directions that is also in an RFC draft is a way to perform signature-based filtering at the edge network, at edge routers, for example, P4-enabled routers. And as far as I know, there is a draft that proposes the BGP flow spec payload matching, and also that can be really smoothly combined with the P4 data plane and filtering really specific signatures at the edge. I hope that I'm in time. Thank you very much for giving me this time slot, and I'm really glad to answer any questions.
Thank you very much. You're perfect in time. Any question, urgent question? Because otherwise, in 5 minutes, we will go to the general discussion. Questions? Anyone? I have a question, Marinus. You're not using P4, right?
We're not using P4, no.
That implies that you can do data plane programming without P4. What is your experience in general?
So Express Data Path is a really mature framework, and a lot of key players are already using it, from Facebook and Cloudflare to even Dropbox, if I recall correctly. This is really similar to writing C applications in C language, and I would say that the concepts are pretty similar with P4. So yeah, it's pretty straightforward. And one of the key, if I could mention that, one of the key things that I want to say is that XDP is really out there, since even virtual interface cards or even Intel interface cards or from other vendors, they actually support it, and you can achieve extremely high packet processing rates. So it's really out there, and it's already built from Linux kernels 14.5, if I recall correctly.
Thank you very much.
Thank you.
For the sake of time, I will now give the floor to Harvey for his own pitch.
All right. Can you see that all right?
Yeah, thanks.
Okay, I'll just present a few slides, but I think it's a great complement to many of the developments, really compelling developments that were shown today. There's a huge problem space, and many of these developments and systems can be applied, I think, here. So I'd like to say a little bit about the Global Network Advancement Group, and in particular, its Data Intensive Sciences Working Group. And its mission is to meet the needs of the major science programs, but without overly impeding traffic from the larger community that uses our shared network infrastructures, both on continents and across the oceans. of course, one of the main focuses right now is on developing a new computing model, which we're pretty convinced will be needed for the high luminosity LHC. So just a little bit about the Data Intensive Sciences Working Group. As I said, its principal aim is to meet the needs and also meet the challenges which are faced by major data intensive science programs, while making sure that while we build a new system which includes an intelligent data plane and control plane, that one of its goals is to prevent the traffic from these major programs, the HLLHC in particular, from overly impeding or even blocking other traffic. So this working group is a forum for discussion, but also a place to bring together common tools and systems which are of interest in building this new system. And one of the main elements of it, which is a great advantage and is about to start working, is the persistent global testbed, which is using layer 2 virtual circuits with bandwidth guarantees through the SENSE project, actually AutoGoal and SENSE. So we're at the point where we really want to work more together with the so-called blueprint groups that are developing the planning for the high luminosity LHC. And in particular, we're focusing on a new model which treats the network as an integrated part of the overall system and allocation of resources on the same status as the allocation of computing and storage resources, and interface to the data management systems that the experiments have. So the top line message is we need this new kind of system. Given the data volumes which are concerned, for example, CMS is about 350 petabytes per year foreseen for raw. For the analysis objects, 200 petabytes per year, even for the compact so-called mini analysis object data, 30 petabytes. So a small transaction in this environment is about a petabyte and something you'd like to do in a shift, which brings you immediately into the few hundred gigabits per second range. So the requirements of the program of the experiments has been examined, and requirements documents have been written in the last several months, and they express terabit per second flows to the major laboratories, half a terabit a second to the smaller centers, smaller tier 1 centers, and tier 2s have to support already 400 gigabits per second for hours to support this working set refresh at the petabyte level. So I already mentioned building the new computing model. There is time to develop this system, but Run 3, which is coming about probably already next spring, will be a great opportunity to test many of these developments as we do them in a working environment while we're taking data. And so that's coming up.
I'm sorry to interrupt you, but I've seen you have still 15 slides. And
oh, yeah. No,
have a couple of minutes more. Otherwise, we eat up all the discussion time.
Yeah,
so
okay. Let me just do this one. So this is some of the key developments of the last year. The AutoGoal SENSE testbed is about to start its persistent operation. There have been upgraded parts of the infrastructure beyond 100 gig, for example, between SurfNet and CERN, 2x100 gig from Caltech to UCSD, and 2x100 gig Caltech to Sunnyvale. We're launching the use of P4 and P4 capable switches and free router at Caltech, UCSD, and soon, and also Starlight, and soon Tennessee Tech. We began working with UCSD and the Pacific Research Platform and Reservoir Labs on the use of their gradient graph decision support tools with the goal of impactful flow, actually flow group identification, flow and or path adjustments, congestion detection, and resolution, and multiple SLAs. P4 is extremely compelling to us because it's the only thing that allows us to have stateful user-defined labels on flow groups and to help to use those in order to have very stateful decisions. We have multiple submissions for the Network Research Exhibition to Supercomputing 21. Okay, so that's it. And there are more slides. On the first slide, at the bottom, you'll see a link to a larger set of slides.
Thanks a lot, Harvey, for being so concise at the end. So essentially, a question for me, you said you understand the possibilities of future collaboration through the use of a distributed environment with the right type of hardware and connectivity, am I right?
Yeah, I didn't catch the end of the question.
Sorry, I'm asking you if you consider these capabilities to collaborate and develop solutions together based on the existence of a distributed testbed, essentially with the right type of hardware, right type of connectivity.
Oh, very much so. I'm encouraged by many things, not only today, but looking at the P4 ecosystem, how it's developing. This P4 integrated network stack is very compelling so that we can spread out by not replacing every switch by P4 capable switch, but by running switches that are running Sonic OS, we could have a very wide footprint and have a widespread intelligent data plane and control plane.
Yeah, just as an introduction also to the discussion we are having now, what are the type of manipulation or control you think would be added, you would like to have in your network that are based on this low-level data plane?
Oh, yes.
Routing, do you want to do other type of monitoring, for example, just to stimulate the discussion? Thanks, Mark.
Oh, yes. I mean, the point is, it's very stateful. I mean, I have a data center analog, which I'm thinking of. It has 4 to 6 classes of work analogous to queues. We have to balance the work between queues. The basic assumption is that we're going to have much more network demand than we have capacity. Given the costs right now and the way costs are evolving and the way the requirements have been set, and the fact that those requirements only take into account the largest organized parts of the overall operation, I think we're going to be working in a very constrained environment. So you have things like classes of work, you have path selection that has both policy elements and has, of course, performance and reliability elements. You have policies which are based on geography, that you prefer that certain flows go certain ways. And all of this can be expressed in terms of the user-defined headers and defined state. And many of the things we heard today were very capable of dealing with state and taking action. And this is essentially a perfect match to a very complex and very important problem.
I open the floor now for discussion. I don't know, Tim and Ivana, if you
yeah, thank you, Mara. I was just going to say, perhaps there are people on the call. There's about 30 people here who have some P4 or data plane programming solution deployed in their networks today that wants to say something about it, or do we have anyone in that position with production use other than the speakers we've heard? I mean, if not, the fact that there's 30 people here shows there's certainly interest in doing that. So I guess the follow-up question would be why you're not doing that. What are the blockers? Why are you not yet in a position to do it? What would help?
I wouldn't call it production yet. We're in the exploration phase at this point. One of the limiting factors is P4 compiler licensing issues. If you don't have a NDA with NVIDIA and Xilinx, good luck. So
in the GÉANT project, that's something we've had to deal with. I guess we can say that there are NDAs involved with having signed an NDA. I mean, the other issue is even distributing code that you then compiled requires a separate type of agreement as well, which we've now arranged project-wide for the GÉANT project. But it's, yeah, that's a challenge, and it would be good if the vendors were more open about this. That would certainly help with the sharing of ideas between the NRENs and the research and education environment. But we had that challenge with Barefoot, and now with Intel, as things move to them, it's a challenge, shall we say.
So Harvey provided us with a SN3700, and we were able to, luckily, we have NDAs with NVIDIA, and so we got their compiler stack, but we were not allowed to share it with anybody that doesn't have that NDA. So we do have a pipeline set up, and we're getting close to being able to do testing across the wide area. But yeah, this is all new.
So I think this is a critical point, because a couple of weeks ago, I tried to follow up on the entire P4 ecosystem, and you see there are a lot of strong developments in the core on certain tools. When it comes to solution pieces, there are some interesting pieces, but it's not kind of taking off. And so what's critical now is whether those solutions are all put into products which are proprietary, even though the core and the functions and some tools are open source.
Yeah, it's a very good question.
Maybe a comment from you about the complexity of the algorithms. Do you find any issues or any independent, which is NVIDIA or others? Because more or less, I think there is two areas that I see needing development. One is, of course, the hardware and the NDA and things like that. But the other hand is, okay, I have now these capabilities. What should I do and which type of algorithm? Which is the balance also between what should be done in the data plane, and as we have heard, what should be done outside the data plane in terms of machine learning, for example, your experience?
I thought Yatish's presentation was very interesting in that respect. By putting an edge system with FPGA right next to some of the core routers, you can do very interesting things and get past at least some of the performance issues and limitations.
Yeah, that's the important point in my opinion, because now, for example, in Europe, we are talking about going to terabit connectivity for HPC, high performance computing, and other sites. But it's clear that you can't have easily routers with tens of terabit interface at the packet level. So I think probably architecture will be based on a right balance between optical connectivity, lower layers, and switched packet or IP switched, so IP and non-IP if you want. And so that can reduce drastically the cost of routers interfaces. But nonetheless, then the monitoring issue becomes important at the optical layer. The good thing is that in principle, what I described about it can be applied to any type of bit stream or any type of interface. And that can be a plus in terms of optical network.
An interesting question.
Marino just closed the microphone, but it was nice to hear someone laughing.
Yeah, the network, I mean, the whole performance aspect is a very interesting one. I mean, in your work, Mauro, it seems that perhaps it's more likely that you'd want to signal to inspect certain patterns of traffic or flows of traffic at high speed rather than trying to get everything. It's clear, the volume of data that's being exported is massive, but to be able to sort of surgically look at specific flows is a very appealing aspect of it.
Yeah, I agree. It boils down to the fact that you can really choose the flow that you are interested in, or a specific router with a specific switch, and then go in depth in the analysis of what is happening there. And that's, my opinion, what the data plane programming also uses implementing.
So we're deploying on the Pacific Research Platform the P4 capable switch. Our distributed cluster is already doing telemetry from all of the endpoints. We install SFlow and a whole bunch of other containers on all the nodes. And so we can see the science workflows, and all the measurement tools are integrated into the same environment: Prometheus, Grafana, Thanos. And then we have in-mon traffic sentinel aggregating all the SFlow from the hosts and the switches. And so we have a very, very wide view of the network. We also install perf sonar. And so we have an end-to-end trace route mesh of the entire network. And so when we add P4 capabilities on top of this, we have the all the metadata available from gradient graph, from reservoir labs that are consuming all these bits. And so we're going to be presenting these as REST APIs for other tools to consume to make the decisions that are then given to the P4 paths. So it's a good environment because we already have the measuring and monitoring tools installed, and we're just adding P4 on top.
Well, so an interesting problem we're getting into is the relative role of P4 and this system-wide tool, gradient graph from reservoir labs. So you can get information about recommendations for alternative paths and or which are the constraining flows and define flow groups. But we need, of course, we use P4 to actually do some of the execution. And also some of the in-depth network information need not be put inside the tool, the gradient graph tool, but rather be another part of the decision engines coming from the P4 code. Some of the things I saw today were very interesting to handle certain things or new possibilities. So for example, a general flow redirector or flow group redirector would be one application. Another would be, can I subscribe to certain groups of flows? And by subscribe, I mean I want certain actions to be taken on those groups.
Yes, that certainly looks very interesting from the point of view of the work that's happening, as you know, in the WLCG group with the packet marking and so on. There's lots of potential there.
Any other comment or from the floor? I don't know, from other people working on this environment, or interest? What are they interested in?
So I guess one question, Mauro, is we're almost, I think we're finishing in 3 or 4 minutes. The question is, where do the people that are here today, where can we follow up and discuss things further, share things? I guess you'll send, or Xavier will send, a follow-up email to the attendees just to remind them where the slides are, make sure all the material's up. But is there a place where we can continue to discuss things and look for more collaboration?
There is a mailing list on LinkedIn DPP that I said. There is a mailing list in the Slack in our channel, GÉANT. So we will put those, but I think we need to find the interesting commonalities in what we are doing. One of the things, my last comment is, I think we need to have end-to-end monitoring in some way in these cases. And I don't see that it's not possible because of hardware lack. I think it's more complex because of the way we may not be able to exchange information. And so what should we do when we want to monitor things end-to-end? Just place end-to-end P4 switches and then lead to them, or instead reach a balance between what we can get from another domain or another domain. So I think that there are practical issues that may help us in not just having monitoring for the sake of monitoring, but mostly debugging our own networks. If you need to really understand and pinpoint a site which has issues, let's say, let me allow that, then that distributed monitoring is needed, and we are going to multi-domain monitoring.
Yeah, and it makes sense initially to do the monitoring. Then you have to figure out the data sharing aspects. And then secondly, to do potentially the type of steering and control that Harvey was mentioning.
One approach that we're taking is we're running everything in Kubernetes, and that allows us to do namespace federation between clusters. One of the things that we've been doing a lot of work on is the smart NIC. We're able to run K3s Kubernetes on the NIC, which allows us to join the edge device to another cluster and then federate it between other universities. So you can create a federated layer for control. That it's a namespace based peer-to-peer federation using a tool called Admiralty. There's several Kubernetes federation tools available at this point.
That's very important. I think we didn't discuss the possibility of local data centers monitoring or use in the data center using the one environment. The two are merging, so it's difficult to distinguish between them. But I think that will be done. We need to consider both these discussions.
Yes, and it's been very good to have people here from the US side of the R&E community. So hopefully there are things we can do together. I guess Harvey is always going to welcome people to join the GNAG group and contribute there as well.
Yes, definitely.
Question for you, John. With P4, we are facing the possibility to and the opportunity to reinvent how we are doing network management. And usually, the traditional way to do this is to, for example, use SNMP and gather link load from the network device. So essentially, this is a polling that occurs every 5 minutes. So you will have 86 400 samples of polling related to the time interface. When we are with P4 and other new ways to do network management, you won't have this granularity that is set to 5 minutes. You will have to face a tremendous amount of raw data coming from the network, and Tim was mentioning the way to pinpoint surgically what happened to the network, what to do with this specific particular tiny flow among the myriads of flow. And my question is related to Kubernetes. How do you have existing building blocks that provide analytics functionality, like searching? I mean, you have, for example, a way to scale horizontally, so that at least we can reuse these components and make and instantiate them in our worker nodes, in our Kubernetes nodes, and make sure that we can scale horizontally, so we can have a decent, I would say, initially system to put our raw data coming from the various experiments that maybe Mauro or Marinos and even ourselves can pour into. I mean, do you have this type of image already?
Is this a question for me, Frederick?
Yes.
Okay, so yeah, we set up a 7-node elastic stack made up of PCIe Gen 4 next generation servers, and basically that is set up to ingest and analyze all kinds of data from network telemetry. And so every one of these nodes is connected at 100 gigabit a second to our core currently and can have 200 gigabit a second if needed. They have OCP3 slots on the back that are unused.
What is the level of network management information you are aggregating from your network? What is
SFlow
the
is
scale?
what we're grabbing.
Yeah, but what is the scales? 1 million flows, 2 million, 3 millions?
Geez, I don't know.
Okay, no, the
You just
idea was to
collected.
see
I
how
don't have time to analyze it.
no. The idea was to see what would be the scale of a network that is powered by 100 gig, and what would be the scale where you expect to receive on your Kubernetes cluster that has this elastic ELK analytics blocks ready to receive this data. So it was just to have an idea from my part. Because we are not working at the same scale, I think.
It's limited by our ingress at 200 gigabit a second, but that's going to change as we get the terabit network fabric coming in.
Yeah, from the architectural point of view, I want to make a couple of comments here. We don't want to deal with millions of flows. Nobody does, and nobody has to. When you have a large base of users, it's really exceptional to have to look at a single flow. So you can treat the traffic, as an aggregate, flows as large aggregates. So smart traffic and the analog in networks and smart traffic is like that. Then we have a science organization. We have all these classes and priorities and policies and so on. We have more than 100,000 ports open. But so what? I mean, we don't want to track individual flows. We want to define flow groups. And instead of dealing with hundreds of thousands of entities, we want to deal with tens to hundreds of entities. Did that make sense?
I think that we will have to deal with that, because what we have realized in our environment and at the GÉANT network is that we need to automate. And if you start automating, then the scalability of the systems has a boost. And so you may consider a certain amount of challenges that previously were not reachable, were not able to solve. But if you automate something, and the automate may be using the data plane, for sure your scalability issues goes to a factor of, let's say, 100. Not in thousands, not millions. So we still have a scalability issues there, but probably you may consider the feasibility of doing more than what you think you can do now manually with your environment. And I think that is a value, because now we are growing in scale and we are going deeper in time. So there are various axes in which you are scaling. And of course, you need to find the right balance. But automation is one of those. And then the analysis of what you do is also an important part. And then that ends up in big data.
And don't forget the visualization part. That was actually the primary goal of my team, is to create a global network visualization tool that consumes all of these REST APIs. And we've chosen Unreal Engine as our multiplayer game engine to display this in. And so we're going to produce plugins, free plugins that you can load into Unreal that consume Netbox, consume Esmond-D, consume all these tools, and then understand node graphs and then lay them out on the globe. So open tools for network visualization is what was where I started at this project.
So another fear people have is the overwhelming volume of data, which I think is also not necessary. So when one has analysis tools, one should run them and, catalog network events, represent flows as time series, parameters, not binary data, that you collected. And so past a certain time interval, you don't have to store exabytes of raw data for the network monitoring.
Okay. We are 4:07 p.m. So I think that I would like to close here. Thanks a lot to all the speakers and for the interesting discussion. We will send a mail and we will try to catch up because I think it's really needed to share the knowledge more, share the technology. Technology is important. I'm technology at heart, but my brain says that we have to exchange also knowledge. And so thanks a lot for the discussion. I will leave to Ivana and Tim the final word as the second 6 speakers. Ivana, Tim.
I would really like to thank everyone for joining today, particularly our speakers today. It has been very interesting and we've seen different work ongoing, and it is really great to hear cross-pointing on work from different teams. So it looks like one thing that we have managed to accomplish all together is to create a community around this work. So many thanks everyone for participation, and looking forward for a future collaboration.
Thanks a lot. See you soon.
Thank you.
Thank you. Bye.
Bye.
Bye.